Anna Retore will talk about new integrable deformations for AdS2 and AdS3 R-matrices.
Okay, so first of all, I'd like to thank the organizers for this invitation and for organizing this very nice conference. And today I will talk about a project that we actually finished the paper this week. So it's supposed to arrive to appear in archive tomorrow. So I will talk about these new integrable deformations of AdS2 and AdS3 R-matrices that we found. So it's a joint project. So the R-matrices were found in this paper with Marius, Chiara, Anton, and Paul at Trinity College. And now we are studying these deformations and trying to understand better how they work. So this is what I will show today. So the plan for the talk is to start with some introduction and motivation. And then explain the method we use it to find these deformations. Show the deformations and explain the symmetries that they have. And then some conclusions and open questions. Please interrupt me if you have any questions at any moment. So we saw in both Alessandro's and Leander talks already about these AdS3 integrability. And so I will not talk too much about the original symmetries at the beginning of the talk, since they already mentioned it. But so I think everybody here kind of knows that this integrability appears not only in AdS5, but also in this lower dimensional like AdS3 and AdS2. And we are trying to find deformations of these lower dimensional ones. So their matrix for AdS3 times S3 times T4, for example, was obtained by, you consider that these off-shell symmetries obtained for the nonlinear sigma model, and the symmetries that are responsible for the integrability. So they assumed that this would remain at quantum level, and this was enough to fix the S matrix up to the dressing factor. And if we focus in this SU1/1 centrally extended, the 2 copies sector, we can write this S matrix in these 4 blocks, so depending on the left and right. And oops. And so this satisfies the Yang-Baxter. And each of these blocks are embeddings of 4x4 R-matrices. And then the diagonal blocks come from 4x4 regular matrices. So when you put the 2 spectral parameters equal, you get permutation. So, but these off-diagonal blocks, they are not regular. This is important to mention because with the method I've explained, we first get these diagonal blocks and then we use something else to get the other 2. So for AdS3, the diagonal blocks are regular 6-vertex R-matrices. So again, these they are regular, so they are proportional to P when the spectral parameters are the same. So you have only scatterings like these. So spin is conserved. You don't have like 2 bosons going to 2 fermions, for example. But for AdS2, like the massive AdS2, it's actually an 8-vertex regular R-matrix. So we have these 2 extra elements here, and this means that these 2 scatterings are also allowed. So you can go from 2 bosons to 2 fermions, or 2 fermions to 2 bosons as well. Well, I'm showing this because we highly rely on a few of these things to the method. So our goal was to find the most general integrable deformations of AdS3 and AdS2 of this format, and the strategy. It basically will follow a very different approach than the one that it was followed to find the original ones. We don't know, for example, which sigma model is related to these yet, to the deformations we found. And a priori, we have no idea about the symmetries. So what we'll do is very simple, is we try to find all the possible solutions of non-difference form of the Yang-Baxter of this, with this form. So we want only the cases that preserve fermion number, because we still want to interpret these as some supersymmetric model. And we don't want, like, I don't know, a fermion and a boson going to two fermions, for example. And the method works only for regular ones. So we'll try to find the diagonal blocks first using this. So we'll find, the idea is we find all the solutions of this type, and then we try to embed these known models in the ones we found and see if it's possible or not. If it's possible and we have something left, in principle, we have a deformation. And at the end, we try to study the symmetries. We actually, like, when we started this project, we had other thing in mind as well, like Paul, Anton, and Marius, they had found constructed this new method to find solutions of Yang-Baxter, this boosted automorphism method. And with this, they had managed to classify, like, all the by four solutions of difference form. So they kind of found a method to classify the solutions of the Yang-Baxter that worked for difference form. So with this project, we kind of put two things together. We were trying to generalize this method for non-difference form, and like a 4x4 is a very good place to start if you wanna. It's the simplest thing you can start. But we also wanted to find this deformation, so we kind of put the two things together and try to. Here's like a spoiler what we find, and then I'll explain better at the end. But for the AdS3, we find two deformations. One is actually an elliptic deformation, so it's an 8-vertex deformation of AdS3, one parametric deformation, and it has crossing symmetry, so in principle it's physical. It has braiding as well. The other one is actually a functional deformation in the sense that we have some general function instead of x plus and x minus, but because we don't know much about these at the beginning, we don't have a way to fix them. So they are kind of general, as I will show. It's not very clear now, but I hope it will be along the talk. And this is also crossing symmetric. And he found an elliptic deformation of AdS2, but massive AdS2. That's actually not crossing symmetric, but has some very nice properties that different properties. And we have the hope that maybe if you consider the massless modes as well, this would recover the.
So I was wondering, probably you will explain it, but how can you know if something is crossing symmetric if you don't know what are the symmetries and therefore what is the charge conjugation?
Oh, no, we just found some crossing equations, basically, in the sense that it's possible to define some crossing equations just because we constructed the R-matrix. So we can, in principle, write the crossing conditions and solve for the system. And I will show explicitly for some.
I will ask you again after you show it if I don't understand it. Thanks.
Okay.
I'll wait.
Sure. Okay, so the first step then is to find all the solutions of non-difference form of Yang-Baxter. So in order to do this, we'll generalize this method now for non-difference form. And the idea is that you start with some ansatz Hamiltonian that's nearest neighbor. And that's your second charge is Q2. And in our case, this will be of this form, because we want that those R's of 8 vertex. And because it's a non-difference form, the Hamiltonian depends on the spectral parameter that I just saw that I put U here and I put theta in the next slide. So sorry, it's just the same thing. But we know, okay, so we start with this Hamiltonian, and we know that if it's a model is integrable, it has to have all these conserved charges that commute. So in principle, a good start is that Q2 commutes with Q3. So this is what we will start, but we don't know the R. So the way we compute this Q3 is to use this boost operator. And this boost operator, in principle, if you look, it doesn't look very well defined for finite chains. I forgot to say, but to find these R's, we consider like a periodic chain. So it doesn't look very well defined, but actually, although this alone is not well defined, this is well defined. So the advantage of this boost operator is that you can generate higher charges from smaller ones. So if you know the Hamiltonian, you can put Q2 here and you find Q3. And this is well defined because the commutator, when you consider the periodic chain and you have all those that sum to infinite, because of the commutator and operators are acting on different sides kind of commute, you just queue all the things that you don't want. So this is well defined. This relation is well defined for us. So with this, we can define Q3. So Q3 is defined in terms of the Hamiltonian. So if we start with that ansatz, depending on all those small h's, you can substitute here and have a Q3 and in terms of those h's as well and the derivatives of them. And then we substitute in Q2 with Q3. And this kind of constrains a lot the Hamiltonian. It's actually constraints enough that you don't need to constrain more. I will say later, but it's and then it's very easy. You can basically solve these ODEs. They're just ODEs. You can solve for these H's. And then you have potentially integrable Hamiltonians, but then, okay, we know that these first two charges commute, but in principle, we need that all of them commute, not only the first two. So we need to compute the R. But to compute the R now is much easier because we know the Hamiltonian is very restricted already. So what we do is to solve Yang-Baxter now for these two boundary conditions. That's basically, we know the Hamiltonian and it's regular. And to do that, it's basically we apply the derivative with respect to U in Yang-Baxter, and then you send V to U, and then you can use in those boundary conditions define this equation, which is a type of Sutherland equation. And you solve this with these boundary conditions, and then you find many solutions. It's like you have to solve like, so for each Hamiltonian you found that's potentially integral, you try to find the R. And so these are just some partial differential equations. For 8-vertex model, it was not so easy. For the 6-vertex was easier, but the 8-vertex was not that easy to solve, but it's possible. And then by solving, you find this R and check that indeed satisfies Yang-Baxter. So for each of those Hamiltonians, we have an R, but not all of them are independent. And then we just use the fact that, and this is because like Yang-Baxter, you can do many transformations in the R matrix that will keep Yang-Baxter invariant, like normalization, renormalization, some discrete, like just transposition and local basis transformations and twists. All these kind of preserve Yang-Baxter, so you can do that. So after we kind of took the solutions we had and compared all of them, we end up with 4 groups of solutions. 2 of 6-vertex and 2 of 8-vertex. So as expected, we found all the known ones. So all the known ones are in the, and but it happens that only 2 of them are important for us when we think in AdS, because the other 2, you cannot embed the AdS models on them. So we will call the 2 that we are using here that are relevant for AdS, 6-vertex B and 8-vertex B, because we call 6-vertex A and 8-vertex A the original one. This is the first one, is the 6-vertex B model. And so what we, as I explained at the beginning, when you have the R matrix, the full R matrix, you have these blocks. So what we try to do now is to deform independently the 2 blocks. So we consider these for like right, and left. We put some indices here. And then we want to lift the models for the whole thing, but we don't know the symmetry. Usually you can use the symmetry to find the left R. And so we will basically use only Yang-Baxters in some sense. So you basically associate each space with a chirality. So you can think as a Yang-Baxter acting in like 3 spaces, mapping to 3 spaces to 3 spaces, and these A, B, and C can be left or right. So with this, you can define 8 Yang-Baxters. And if all of them are satisfied, your full one is satisfied as well. So this is the way we fixed the other blocks, because the other blocks, since they were not regular, this method we constructed doesn't work. So this was the trick we used. So, for example, if you have right, like those spaces like right, left, left, you can construct these, and then these, oops, this left, left is just a copy of that one that we found with our method, but this right, left, we don't know. So the idea is that the one, we propose some ansatz here, and it's actually possible to solve. So we make an ansatz for right, left, for example, and we can solve for it, and then we can do the same for left, right. And the point is that the first 2 Yang-Baxters are kind of automatically satisfied because they are the regular ones, but then we solve 2 others, and we fix this right, left, and left R and left, right, just apart from one functional variables. And then the 4 left Yang-Baxter that were left kind of fix the rest. So it's completely fixed at the end. And then we can check that this full R matrix really indeed satisfy Yang-Baxter as well, which it does. Okay, so now I will start to talk about each deformation separately, and let's discuss a bit what happens. So we assume that left, left, and right, right blocks were independent. Oh.
Sorry, another question on the left, right. So left, right, and right, left are related by a braiding unitarity?
Yes.
And sometimes it is also assumed that there is a Z2 symmetry, like swapping everything left with everything right is a symmetry, so that left, left is equal to right, right. And left, right, and right, left are, well, if not equal, at least related by this symmetry in a simple way. Did you use this last assumption, or did you relax it?
No, we started with, but for the deformations match with the original models, we had to do a twist that kind of messed up a bit the left, left, and right, right blocks. So they are not exactly, we have these, let me see if I wrote here. No, this. So because of this twist, we have these X and Y's. Mm-hmm. Oh, actually, no, I'm saying something. No, actually, they are equal apart from indices. They are like like for this model, right, they are the left, left, and right, right blocks are equal. Yeah, they are. But, and then the right, left ones and left, right. I know they are related by braiding, but I
just wonder whether it's something that you always require to have this sort of extra relation, also for the new models, or you didn't require it, it comes out for this particular case, but in general, you will have something more general.
We try to require that left, left, and right, right were equal, apart from. Okay, for this different. Okay, we started just taking always two, like the right, right, and left, left, like equal. But when we and for this one it worked, but for the other deformation we needed to fix something on the right, right block to make the right, left, and left, right work in a way that the full was so the left, left, and right, right blocks are not completely independent. Mm-hmm. So there is some kind of I don't know if I replied at the end, but maybe I have to.
Yeah, we can look at it later. Yeah, thanks.
Show explicitly, but I don't remember now exactly but we didn't.
It's all right. Okay. We can look at it later.
Okay, I mean, for the pure blocks, you can do this, it works, but for the left, right, this more subtle.
Yeah, we always start with left, left, and right, right, kind of the same apart from the labels, and then we had to fix some things for. Let me. Okay, so we were able to deform these blocks independently, construct the right-left and left-right blocks. And the result is a deformation of AdS of the AdS3 times S3 times T4 and the AdS3 times S3 times S3 times S1. But then we realized that there was this Q deformation by Ben as well. When we check it, this is also a deformation, but it's a kind of a subtle deformation because I will show the map. So if we identify our H1 right with X minus right, X2 right with X right plus, and also do the same with the left ones, and do this identification of X left and Y right, and like all this extra in comparison with this model, they match. So in some sense, and we have the same number of parameters, but we have this H, general, but we have them general because we don't have enough information to fix them. So we don't know how much of a deformation is this because we don't have enough information to, it's kind of a very general H in principle. So in principle could be any function of X of P. So, but it's very hard for us to make statement about this because we don't have more things to restrict it enough. So in some sense, it's quite general.
So sorry, the statement is that then the Yang-Baxter equation is satisfied without necessarily imposing the quadratic constraint between X plus and X minus.
Yeah, we don't need any constraint on these H's, basically.
That's the only thing you're relaxing compared to
yes.
the S matrix of Ben.
But then in principle, these H's could be anything, like in order to satisfy Yang-Baxter can be anything.
Yeah, thanks.
So I'm showing comparison with Ben's deformations because then it already, since his deformation already includes the other two, I compared directly here. And in some sense, this is like, if you think of X plus being related with X minus, it kind of would mean that that the mass depends on the spectral parameter, on the rapidity, and but this like happens to this mixed flux as well. So I think it's okay. And okay, it has we were able to find crossing relations for this. So we tried to find the symmetries then, and then here it's wrong. I just realized that here is R check, not R. But in order to find the symmetries, if it's a symmetry, then this Q with inverted switched spectral parameters times R has to be R times Q. So the idea is that we apply a derivative with respect to U and send V to U. And we have a differential equation. So we will suppose some form for Q. Well, in this case is this Q cross 1 plus U cross Q. I forgot to write them explicitly. And if we assume a form for Q and U, we can kind of fix them using these differential equations. So we start with this Q, where the blocks are like this, and this Q plus and Q minus in the form I showed in the previous slide. And with this, we were able to fix all these things. And then if you see, it depends, all this symmetry depends on these H's, and also in a constant S and T. And we were able to check that there are actually 4 independent supercharges, depending on how we choose this. So here we have this S and T. So it could be 4, there are 4 of them. And these are the coproduct for the central elements. So the point is basically, if we do that map, this comes back to the Q deformation, but honestly, at this point, we don't know what else we can do since we don't to fix those H's or to restrict them more. Okay. Now we like this 8-vertex model. This was actually a very nice surprise for us because when we found it, we expected to be an AdS2 deformation, and it is, but it's actually a deformation of AdS3 as well. So if you see, you have this, we have used this short notation here, like Sn is the Sn of the difference. And then we have this K here. So these are just Jacobi functions. But the point is that if this deformation depends on this K, and when K goes to infinity, it becomes AdS2. And when K goes to 0, it becomes AdS3. We can do a direct map, just sending these parameters to these values, we can find the deformation. We can recover the original models. And for the symmetry for AdS2, massive AdS2, we started with this thing. And actually something very curious will appear for this for the symmetry for AdS2, is that we start with this. And then the first part is quite nice, it's quite usual, but like you can see that this charge is highly dependent on K, on this K, and these omegas can be plus or minus 1, but it's actually quite hard to solve for any value of K. So I just left we just left here kind of some functional equation, but for K equals to 1, for example, that doesn't correspond to any known Ks, your Jacobi functions become trigonometric, and then you can write a nice formula. But in principle, it works for any K. And if you look this U, it actually, you can use it to define if you choose omega 1 going to minus omega 1, you notice that this becomes a U inverse. And then, okay, so if U becomes U inverse, you can define these, use this to define K plus and K minus, depending on the choice of this omega. And we just fixed omega 2 as one of the values. It doesn't really matter for omega 2. And then we found something like this. So for K equals to 0, you recover the original charges. And so in principle, all this part was like, it seemed like nothing was happening. It's like we have this explicit like representation changes, but not, but then when you start to look to higher charges, like if you use RTT to focus in higher charges, okay, so we expand here in powers of U. We find that this K drops out completely at first 2 orders. So we were kind of, oh, okay, maybe it's just a representation thing. So at first order, U is central. We see that U is central. At second order, we actually obtain the usual PS1/1 central extended, again without any K dependence. So the first level Yang actually is the same as in Ben and Alessandro's paper, and from 2015. But actually at the next level, the second level, Yangian, it kind of decay starts to appear in the structural constants of these, and it kind of, there is no way to absorb it. For example, one check we did is that like AdS2 is known to have this evaluation representation. This model doesn't. So you cannot kind of absorb this K in a new like energy, mass and momentum kind of. So it looks like an actual deformation, but this Yangian looks quite strange because it has this K dependence on the, so we don't know if this is some kind of new type of Yangian, or we don't know honestly what's going on, but it looks quite different and interesting. Something is happening. The problem is that if we took into account only the massive modes, then we don't have crossing symmetry. There's no way to write crossing equations that make sense. So our hope is that if somebody computes the massless modes as well, like when you have the full thing, maybe these things will rearrange in a nice way that would make you have crossing, but at this point we don't know.
So if I may, I'm a little bit confused because crossing, so if I understand correctly, you identified at least in this particular two particle representations, you notice the algebra, basically the supercharges in this representation, right? You work them out, and also the central charges and so on. And I mean, crossing usually either relates a representation to itself, or it relates a representation to a conjugate representation. So the first thing that you should work out, I guess, is whether you have conjugate representations or not. I'm not sure what the massless modes would sort of do, because at least normally the massless modes don't talk at all through crossing. I mean, left is conjugated to the right, and massless is conjugated, loosely speaking, to itself. So I don't see our reshuffling, you know, would involve also the massless modes if this thing is a deformation. I think that maybe, I'm not sure, I've not seen the computation, but there are many subtleties in defining the crossing transformation, because not only you have to identify the algebra and the central charges, but also you have to decide what is the momentum and what is the energy. And those are the things that should change sign when you cross. So if now you have a different notion of what is the momentum, then it's sort of tricky to say exactly what crossing should do, right? So again, I'm not saying I've not seen exactly what you have done, but I can think of many subtleties that maybe I would check before thinking of the massless modes, honestly, in this case.
Okay, maybe we can talk then, like at some point. It would be nice if, yeah, because I think we did in a bit naive way, crossing, like wrote the crossing expressions and tried to fix for general K. And then at the beginning, we were not finding anything. And then we thought the problem was because of the Jacobi functions, that maybe we're messing up something. We were not realizing, managing to simplify things and often Mathematica, and things were not, you never find something useful. But then we did this limit K going to 1. That's not a null model, but all the Jacobi functions become trigonometric. And then it's very obvious that kind of doesn't work. But I don't know, maybe we missed something.
Maybe I can just make a quick comment. So if I understand correctly from what you've said, you've got an R matrix that interpolates from AdS2 in one limit to the, say, the left block of AdS3.
At this part, yeah, but actually it works for the whole.
Maybe, can you just?
Oh, sorry. It actually works for the. It's a limit of the. We managed to lift the model, so at level of AdS3, it's actually the formation of the full thing.
Oh no, okay. I'm just taking a simpler.
Okay. So yeah.
So you have this 8 vertex thing that interpolates from AdS2 to the left block of AdS3.
Yes.
AdS2 is kind of invariant under crossing by itself, whereas the left block of AdS3 would go to the left-right block under crossing. So yeah, I can believe you that there is some issue with crossing. Anyway, that is different.
Yeah, because actually when we took this other deformation I show now, like when we interpret this deformation as a deformation of AdS3, and if you take just one block, it's much trickier. It's not obvious at all. But we can. But I understand what you're saying, yeah. But as I said, the biggest surprise was that when we compared the models with the undeformed ones, it kind of was a deformation of AdS3, and we tried to deform the blocks independently, and we managed in some sense. And this is a deformation of the usual of these undeformed models, but it's not a deformation of this Q deformed model. So I wrote it again here. So for K going to 0, these two matrix elements disappear, and like you can get a map, a very nice direct map between this AdS3 times S3 times S1 in our model. So we can map it to it just by making these choices. This tau is just a sign. And yeah, like for k going to 0, this works fine. So actually, if we look here, we managed to, so these G's, G right, and we have a G right and a G left. But this eta, for example, we had put an index on this eta, and it actually, we are forced to relate eta left and eta right by a factor of pi. So both the kind of these blocks can be deformed independently, but some things you still have to choose. This is what I was referring when Alessandro asked the first question. So here you can write the crossing equations very easily for the full block. Things kind of rearrange nicely when you have the full one. And then it's very simple. This k is just this elliptic integral of the first kind, which is basically the pi of the Jacobi function. So it's the thing that your Jacobi functions are periodic on it when you have multiples of this thing. And this is one example of one of the crossing equations. So there are a few more, but this is, so it looks quite ugly. So it depends a lot on this. So all these Jacobi functions depend on k. But like, as I said, like the left and right blocks are basically the same as the AdS2. So we kind of learned about the symmetry a bit already. Oh, there's a typo here. This was centrally extended. But actually only two supercharges survived. This k kind of broke one of the PSU 1/1 centrally extended. So it kind of broke. So it seems, and when you send k to 0, all nicely comes back to the original ones. But yeah, this k seems to bring two of the charges, of the two supercharges. Okay, so we were actually thinking if this could be a hint to construct a sigma model, knowing that it breaks part of the symmetries could be a hint, but we don't, because this is one of the questions we are more curious to know if there is a sigma model related with this vertex deformation, but this is kind of the only hint we have. Kind of, there is something that breaks in comparison, like half of the symmetry is gone. Okay, so summarizing, we have these two deformations of the AdS3. One is this function deformation, that's actually deformation of this Q-deformed model as well, and it has crossing. This elliptic one is this 8 vertex that I showed, this 8 vertex deformation of AdS3, and it also has crossing. And this AdS2 one is elliptic as well, and like in principle we think there's no crossing, but if it has, it's better. So we can discuss later. So I just left some questions here that we had thought about these massless modes, but yeah, maybe if we can do something else, and if this deformation is physical, it would be much better. We are actually curious to see what this 6 vertex deformation, how this 6 vertex deformations connects with this 3 parametric deformation that Fiona and her collaborators, like Alessandro and like they found. It's like in some sense we kind of seem to agree with what they found. They found that there is only like a 3-level S matrix. So in some sense we didn't find a deformation with 3 parameters. We only found with 2 in this functional thing. So somehow we kind of seem to be finding that's not possible to have the Q3, but I don't know. So we are trying to understand this part. And I think the main question that says is if there is a sigma model with this 8 vertex deformation of AdS3. Thank you.
Questions?
So about this 8 vertex, more sort of mysterious deformation. Do I understand correctly that at some point you have basically it's related to AdS3 and you have 4 supercharges essentially, and you have a short representation with some shortening condition. And then for generic K, 2 of the supercharges are not there anymore.
2 of the charges disappear, yeah.
Okay, so the algebra basically changes as soon as there is a finite K, essentially, a finite amount of K. Is that correct?
I think so,
And
yes.
And they are just not there. They're not. I mean, you cannot see whether the algebra is somehow deformed in some way.
Yeah, they don't satisfy things nicely. Like there is no way to satisfy the equations with them there. So, and when you send K to 0, you kind of recover all of them are back, kind of. So there is no way to define them in a way that they are the 2 supercharges, like they satisfy the proper relations.
So in a way, I guess the limit towards AdS3 is much more singular than the one towards AdS2. If that's,
the what? Sorry?
Taking the limit towards AdS3 is more singular than taking the limit towards AdS2, in a sense.
In this sense, yes, but actually the limit for AdS3 is immediate, like you don't need to be careful or anything, and the limit for AdS2, you have to do some transformations, you have to be very careful to take it properly. If you do it in the wrong order, so it's very subtle, you have to be very schematic, like structured in the way you take the limit, otherwise it just doesn't work. So I can see why you are saying that, but for us it was much trickier, it was much more, because of when you send K to infinity, you have to be very careful with the Jacobi functions, using some identities and some things in a very schematic, like in a very strategic way.
Just a quick about this 8 vertex AdS2.
Yes.
So you say that you can get the left or the right out of AdS3 by taking K to 0. Is that, yeah, that's good. Is there any way of getting the right-left out of it?
For AdS2?
So this 8 vertex model that you have.
For AdS3?
No, the AdS2, no, for AdS2, I guess. Just the 8 vertex.
For AdS2, we just look at the 4x4 blocks.
Just the 4x4
the 4x4 block, yeah.
So is there some limit in K that you can take to get the right-left block out or not? So
I don't see how. Oh no, I don't see how we.
Okay.
Kind of
about this, if you try to do the same trick of trying to just write a Yang-Baxter equation with the left and the right and try to solve it, would it give you anything?
From the beginning?
For finite K, right? For finite K, you say I have this guy and I think of it as left block. I have this guy, I think of it as a right block.
I have an argument for not working. And this is, you are just proposing to put and then putting something general on and try to fix these extra things, right?
Yeah.
This would not work because the full one is not regular as a whole, because the right, left, like when you send U to V, these blocks will not disappear in, so in the method works only for regular R-matrices. We are only able to use this method to find regular ones, and the full R-matrices are never regular, I think.
Okay. Yeah, I believe you. I don't see it.
Sorry, I don't know if I replied.
I don't see immediately the fact that you can only do it for regular, but yeah, if that's so, that's.
Yeah, like because this boost, like it only works for regular. It's constructed. The method is constructed in a way that is only.
you don't understand for arbitrary k. You can only understand for three limits like 0, 1, and infinity. If you take arbitrary amount, as you say, you don't have this information.
Our question.
It's about this final comment, one of your concluding points. Could you just say a bit more about this 3-parameter deformation? And I didn't completely understand the punchline of what you were saying. You are saying that it does not fit into your...
No, I think it fits very well in what we have, because then we don't have we couldn't find a third parameter, like it's there is no 3-parameter there, unless it's hidden somewhere in this H, but we don't know how to. So it kind of looks like we are just recovering, kind of matching the results they found, because like they also found that's not possible to. So my guess would be that this deformation doesn't hold at quantum level, maybe this Q3, but this is a guess.
You say you think it's not integrable at the quantum level or something?
It could be like that's a guess, because since we didn't find, in principle, this should be very general the way we did. You should be able to embed any possible transformation that is, because we kind of found all the solutions of this type of Yang-Baxter in a schema, very I forgot the word in English, but it's like it's a very well put. I don't see how we would have lost where we could have lost these.
Okay, I'd be very interested to discuss more.
Maybe discuss. Yes.
It's kind of very interesting. Did you want to?
I just wanted to comment on the comment, I guess, and say that at least maybe Fiona can also add something, but at least when we were looking at this 3-parameter, our feeling was that we were not being smart enough to find some all loop way of understanding it, but we didn't see an immediate reason why something would go wrong at the quantum level. So there is just a possibility that is somehow a quite different beast from, I mean, we had an obvious guess for what it could have been. We wanted to check that guess and that didn't work. And the other obvious thing didn't work. And I don't know if there is just, you know, some very strange way of realizing the symmetry that escaped us. And strictly speaking, I should also say you are working with a single representation, right? The whole thing is a tensor product for AdS3 of 2 blocks, which need not be the same, and you know, all sort of mayhem might ensue. So I mean, it's very subtle, I would say.
Okay.
And then again, if somebody wants to do a one-loop calculation to see if it satisfies the Yang-Baxter equation.
Not me.
Other question? If not, let's make an again.